Okay, off we go. Welcome back. Hope everybody's doing well. Attendance quiz, attendance code, all that. Here it is. Clock's ticking. Let's see here. So reminder, last time we were talking about this idea of what to do if your domain is dimensionally awkward, right? It's the wrong dimensional critter for the dimension of the world that it lives in. And how do you deal with that? Regular old Riemann sums, like we've talked about in the past, just don't work. They don't fit the problem, right? So what do we do? And well, we've made up a new idea, new kind of a Riemann sum for which we have a new notation and a new terminology. So we define in particular this thing called a scalar line integral. All right. And then there's the question, how would we compute such a thing, right? And we observe that, golly, it's a lot like change of variables. Now, it's not exactly, right? Change of variables. The two domain, the domain and the target have the same dimension. That you'll notice every change of variables question we did has this feature. This does not. So we can't just say change of variables, but strategically, it's all the same basic ideas, right? So in this case, the idea of viewing your undesirable domain as an image is literally a parameterization. So instead of instead of pulling back through a change of variables function, we're just going to be pulling back through a parameterization. Okay, and we wrote down the details for that. So how do we find a stretching factor, for example? Well, the stretching factor is speed. Distance per unit time is what relates distance to time, right? Convenient, familiar. Very nice. And then we did an example. We kind of sort of four examples in parallel. We talked through two of them of how you put this into action. And what I will point out about this, it's very plug and chug, right? It's we've got an explicit formula here. Where did it go? Here it is. We got an explicit formula. If you want to compute a scalar line integral by pulling back through a parameterization, bam, there it is. Right? And just make sure you know what all these things mean, and off you go. Okay. Okay, let's see. So we're going to do one more of these before we move on to the sort of the next concept. This is another sort of semi-real world. Oh gosh, excuse me. Semi-real world example. You've got a fence that's sitting on the unit circle. Right, so you got your unit circle here like this, and this is sort of a blown up sort of portion of it. And that unit circle, there is a fence sitting on top. I'm drawing what I'm going to casually refer to as pickets, right? But they're not actually the actual pickets. The point is these are little ds, little pieces of the curve, and how much of the fence sits on top of said little ds piece of the curve. Okay. All right. So I argue as follows. If you're interested in the total area, right, the total area, pretty reasonable case, I think, is just the sum of the areas of the pickets. Right? If you just look at, again, these, what I'm loosely calling pickets. You add up all of those little pieces of area, you'll get the total area. Right? Reasonable breakdown. Okay, great. What's the area of one of these pickets? Well, it's height times the length of the base here. Reasonable case, right? Is everybody comfortable with that? Height times base gives you the area. And then we notice, this length of a piece of let's say it this way, the length of the base is the length of our little differential piece of the curve, ds, and check it out, we now have a scalar line integral describing the area we're trying to compute, and now we're sort of done with phase one of the problem. Right, we've turned the question into a Riemann sum. And now it's on to how do I turn this into an integral I can actually compute, and then, of course, you got to actually compute it. Okay, so to compute one of these things, we have to look at our entire curve. That's the domain for this scalar line integral, and we've got to parameterize it and pull back through that parameterization. Again, plug and chug like the several we've done previously. Good news, it's easy to parameterize. We've parameterized the unit circle many times. Here you go. Nothing to it, our old friend. And everything else is kind of downhill. You take the derivative to get the velocity. You take the magnitude to get the speed. Don't forget that when you do the pullback, you have to insert that speed as your stretching factor. Right, and everything else is just plugging in. So in particular, if I can get this thing to cooperate, here we go. What do we do with the integrand height? Right, well that's given to us. It's x plus 2 over 5. And then there's this ever-present question, what do I do with the x? Right, this is an integral dt. I need to rewrite everything in terms of t. How do I understand x as a function of t? Whatever you're pulling back through. Here we're pulling back through a parameterization. Back earlier in chapter 5, it would have been pulling back through a change of variables function. Whatever you're pulling back through, that tells you how to plug in. And so in particular, this x right there is cosine t. How we doing? Everybody happy with that? Okay. All right, so now we're going to do another example. We're going to feel, as we get started, that this next example is another example of a scalar line integral. And then it's not going to be. So this is a kind of a segue into a different critter that we'll figure out what we're going to call it once we figure out what's going on. And what we're going to have here is we're going to address sort of an old question, that is, how do I compute work? And we, of course, y'all will remember we derived this formula for work back in chapter 1, right? And the idea is that the old high school notion of work, that it's a scalar force times a scalar distance, was fundamentally wrong, fundamentally naive. Forces aren't scalars, they're vectors. Forces have direction. Displacements are not scalars. They're vectors. They have a direction of motion. And when you understand force and displacement as vectors, then work is a dot product. Right? So anyway, old news, chapter 1. Even this had some assumptions that are not very real world. This formula assumes that your force is constant over the entire motion. That's not how reality works usually. Right, sometimes, but not usually. And our displacement may or may not be over a straight path, but again, you certainly can't assume that. So the question we're going to address is that if you have a not straight path, right, and as you move along that not straight path, you have a not constant vector field. Look at how my vector field is highly varied over space. How would I compute this work? In other words, if I have to apply these non-constant forces as I move across this non-straight path, how would I compute the total amount of work? Does everybody see what we're going to try to deal with here? And by the way, this seems like what a great application for our new idea of a scalar line integral, because I have a dimensionally awkward domain. Right? It's a one-dimensional thing in as I have it drawn, two-dimensional setting. And I can chop it up into pieces, and each piece is approximately straight, and the force is approximately constant, and it seems like, therefore, on individual little pieces, the question's relatively easy on each individual piece, and then we add up over all the pieces. Right? So you can see why it seems like, this is going to be perfect. This is yet another success for scalar line integrals. Yeah.
Would this work if it wasn't locally a function of it? Like if it had folded under itself the line?
Oh, yeah, absolutely. So curves are allowed to do kind of whatever. I even kind of, you can see it does kind of fold backwards over here. So any curve, and by the way, the metaphor I like to think of here is imagine this being a mountain road, and imagine that the forces are, maybe those are the directions pointing uphill, and so those are the directions that I have to apply the force to not roll down the hill. You know what I mean? The mountain roads can be all kinds of windy and whatever. Absolutely. Okay, so here, let me recognize before we go on, there's a couple of things about this problem that do not fit well into our scalar line integral construction. One is, I need to know which direction I'm going. Going up the mountain road takes more work than going down the mountain road. That make sense? That is not like painting a fence. Right? If you're painting a fence, it takes the same amount of paint whichever way you go. There really isn't a notion of direction on here. I just have, look, this picket just is. The picket is not going that way, and the picket is not going that way. Does that make sense to everybody? So this is fundamentally different, and that just makes me a little bit worried. The other thing I'll point out is that it's not just a matter of, is it a plus or a minus, right? The amount of work that it takes depends from this point. I can't just say force times distance, right? It really matters that I am going that way specifically and not that way and not that way and not that way and not that way. Right? The shape of the curve matters. And again, not so here. All that matters here is, all right, how long is that? What's the width of this base of this little picket? I don't really care which direction it's going. Right? Okay, so this is really kind of a different situation. Let's be prepared for a little bit of sort of failure of our scalar line integral concept. So, by the way, a little terminology. The fact that the direction matters, the fact that we view this curve as going that way and not that way, we call this an oriented curve. And the choice of which direction we're going along the curve is what we call an orientation on the curve. And it's just a notion of, wait a minute, which way along the curve? I understand along the curve, but which there's two different ways along the curve. Which one is it? Right? So what we call an orientation. So, all right, with all of that established, it does break down actually pretty nicely. And on our little piece of curve, we've got this differential notion of displacement, dr, and we have our field force, and this is approximately straight, and the force is approximately constant, and all that approximate's going to go away in the limit as usual. And so the amount of work it takes to move along that little piece of curve is just the dot product of force and displacement, a la chapter 1. And then if I say, well, the total amount of work is the sum of those little pieces of work, then, all right, well, dW is F dot dr. Okay. All right, now, there's different ways that you can rewrite this expression, and I'm going to show you those in just a couple of minutes, but honestly, this is my favorite of the different ways to write this expression. So I'm going to leave it like this, and this too is a line integral because this is an integral that happens over a curve. By the way, it's a little bit unfortunate terminology. Line, we're kind of accustomed these days to the word line meaning straight line, like high school geometry. Line means straight line, right? In some contexts, line just means any curve. Right? So I don't know if you've ever taken like an art class, but they talk about something called a line drawing, and that just means any sort of curvy path. Anyway, line integral is the term, whether we like it or not. But here, notice that we have a vector integrand, and as I kind of foreshadowed last time, we have a vector differential. That's a new concept for us, right? We've never had an integral before with a vector differential. Is that cool? Okay. All right, so new critter, vector line integral. All right. Now, how do we compute these things? And here's where I'm going to show you some alternative ways to write this. This right here is all just a callback to Chapter 3. And I want to say it was Section 3.2. I think it was Section 3.2. It was at the very start of that section, we talked through these various objects and the relationships between them. And among those observations, we wrote this down, specifically that our vector differential, that dr, that differential for, we didn't realize it at the time, right? But that dr, that is our vector differential. It is the dr from Chapter 3, and there are different ways to write it down that we talked through back in Chapter 3. So with that in mind, we can plug that in. Right? You can take these different alternative forms of dr, and they give you these different alternative forms for how to write a vector line integral. And they all have their advantages and disadvantages. We will talk later about this one. It has some nice advantages, and we'll get to that. Most of the time, though, again, this is my favorite. Let me talk about why I like this one. This is my favorite because, several reasons. First of all, the least pencil strokes, right? That's got to count for something. It's easy to write down. I also like the fact that it is visibly, leaps off the page at you, not a scalar line integral. I think that's a good thing. When you have things that are different, and if that difference matters, let's not confuse them, right? I've always thought that was a weird thing, right? When things are importantly different, let's not use the same term to describe both of them. So this is visibly different. Different notation to represent an importantly different thing. Okay, so there's that. And then last thing I'll point out, the dr here is exactly everything that I know and everything that I need to know about the curve in relation to this question. This dr encapsulates, hey, how big is that piece of curve? It's inside of the dr. It also encapsulates, wait a minute, which direction? Are we going that way? Are we going this way? Are we going that way? Or which direction are we going? That's also wrapped up inside of that dr. So I think there's something, 2 seconds, there's something really elegant about having things that we know about the curve, things that are relevant to the domain, in other words, inside of the differential, and then things that are external, things that are independent of the domain, we have those in the integrand. I think that's a good thing. Yes?
What specifically is capital T?
Capital T is the unit tangent vector. So this, we talked about this back in Chapter 3, 3.2, I'm fairly sure. It's just a unit vector pointing in the direction of... Sorry?
Prime over the length of prime?
Yes, that's right. Yep. Right. Okay. Yeah, so this would, by the way, perhaps be a good time to go back to 3.2 and remind yourself, polish up all your memories of these details that we're going to be using quite a bit at this point. Okay. All right, so anyway, again, my personal favorite. We're about to make lots and lots of use of this one. This one has the advantage that it's already pulled back, right? This is literally an integral on the t-axis on an interval from A to B. On the t-axis, this is single variable plug and chug, which sometimes totally awesome, what we totally need. Right? And I will come back and talk about this more in a minute. In a few minutes, I guess it'll be. But let me talk about one thing I don't like about it. while we're here, this makes it look like we're doing a scalar line integral. Which I think, very importantly, we're not. I think this is a significant point of issue about how this is a different kind of a construction that addresses a different type of a question. And again, if it's not, why do we want to make it look like it is? A personal pet peeve, maybe. Okay. Okay, let's do one. So here's a scenario. So we have a path which is counterclockwise along the top half of the unit circle. That's a path. That's an oriented path. Do keep in mind the presumption here is that we're moving along an oriented path, right? So which direction we're going, let me make this a different color. Which direction we're going along the curve is needed in addition to knowing what the curve is. Right? So you've got to make sure to remember that the orientation matters. Let's see here. And so we want to compute the amount of work that it takes to walk along that path. And here's the force given. And so we're pretty much just going to write down vector line integral. That's kind of what we already derived. There is, however, a little subtlety. This is annoying. This is a reality of the physical world. It's just a little bother. This is nothing to be scared of, but it is, on the other hand, something that matters, and your bridge will fall down if you're not careful about it. So it's a point of physics. If I am holding something that has a weight to it, right? Gravity is pulling my stylus down. There are actually two forces involved. There's the force of gravity on the stylus pulling it down, and then I am applying, forgot to turn that off. I am applying a force upward to oppose that downward force so that my stylus doesn't accelerate toward the ground. Right? Two opposite, what we call equal and opposite, equal in magnitude, opposite in direction. So you have to ask yourself which force is the one that we're going to use. Which force is relevant to what we're doing. So you'll notice that it says that the wind exerts this force. Right? That's what the wind is doing. If the question we're asking, how much work does the wind perform? Right? Then that would be the correct force to use. But notice that's not what the question asks. The question asks, how much work does it take you? The wind is applying its force on you. You are applying a force opposite of the wind. You are applying the force negative F, so the wind doesn't knock you down, knock you over. Right? And very importantly, these are negatives of each other. Is that cool? Everybody see what I'm talking about there? And it's a frustrating, little tedious, little micro issue. But again, you're going to get wrong answers if you don't keep that in mind. So apologies, but you do have to think through this little matter every time you do one of these. Let's see. So we have ourselves our vector line integral now. And how do we compute vector line integrals? Here it is. The way we compute vector line integrals is we parameterize the curve. We compute the R prime that we're going to need in order to use this plug and chug formula. And we plug and chug. Okay, so let's parameterize the curve. We're talking about the top half of the unit circle. The top half of the unit circle is easy to parameterize. There you go. Specifically, it's the top half. It's not the whole unit circle. I get the top half by using just these values of t, 0 to pi, not 2 pi. Is that good? Everybody happy? And and then we take the derivative. That's going to get plugged in. This is all just plugging in. So reminder, don't forget, dr is r prime dt. We just computed r prime. R prime is that. Oh, let's see here. We have our vector field F that was given was y comma negative x. Let's check and make sure we got that right. There it is. F is y comma negative x. Right, so we write that down. Don't forget the minus sign, right? This minus sign that represents the fact that the wind is doing the opposite that we are. That carries through. And then there's the ever-present question. What do we do with x and y? What do I do with this x right here? Okay, well, what am I pulling back through? I'm pulling back through my parameterization, so I've got to look up to here and remind myself x explicitly given in the parameterization, and so x is cosine t. Likewise for y. How we doing? Is everybody happy? Okay. And now we've got it down to a single variable integral, and thankfully it turns out to be a pretty straightforward single variable integral. Nice, easy answer. And as you see, it's all plug and chug. Okay. Let's talk about parameterizations. I'm going to give you the same concern that we did when we were talking about scalar line integrals. Here we have something that exists independent of how you parameterize it. The amount of work it takes me to drive up a mountain road is always the same. It does not matter whether I parameterize that path one way or another way, right? And yet the formula we're using seems to depend on the parameterization, and that's concerning because it shouldn't matter. So thankfully it doesn't matter, except for one part, and that is, don't forget, we're not talking about a regular curve. We are talking about an oriented curve. So we're not just parameterizing a curve. Parameterize however you like, whatever, it's all good. We are parameterizing an oriented curve. You have to parameterize with the correct orientation. Your parameterization has to go the same direction that you're supposed to be going. Does that make sense? Everybody see what I'm talking about here? So that part does matter. Now, thankfully, that's the only part that matters. Right? You get the same value no matter how you parameterize as long as you have the correct orientation. But you do have to have the correct orientation. All right, now let's think about real quick, what if you don't have the correct parameters? What if you parameterize back? Oh, sorry, go ahead.
So when RT gives like the correct orientation, do we mean like clockwise and counterclockwise?
No, it's got nothing to do with that. It's whatever the orientation on the curve is. Right, so if someone says, "Hey, I want you to drive your car on this mountain road," I'm going to do what I'm told. I got to go whatever the direction is that I'm supposed to be going, and that's designated externally. That's arbitrary, right? But it could be anything. Does that make sense? Yeah. So there is no correct, intrinsically correct orientation to curves. Now, I think I know what you're thinking of, and someday. Next week, we will be talking about curves that are boundaries of areas. And then once we start using the word boundary, then the word boundary is a loaded word, and the word boundary specifically means oriented according to certain rules. That may be what you're thinking of. But curves themselves, whatever. They are oriented however they're oriented, and you've got to look for whatever is natural and or given in the statement of the question. Does that make sense? Okay. Yeah, okay, so what if we orient the wrong way? And I'm just going to come back to our picture up here and say, well, look, if you orient the curve the wrong way, then you're going to be going that way instead of that way. The only difference is that your dr vector is going to be exactly wrong. It's wrong, but it's wrong by the very convenient amount of a factor of -1. And that's true on every piece of the curve. And so even though when you parameterize wrong, even though it's wrong, it's highly predictably wrong. It's wrong by a factor of -1. And so that gives us this result here. A little bit of notation first. If we put a minus sign in a superscript, that just means go the other way. It's a very convenient little notation for opposite orientation of whatever C is. And with that the case, if you are looking at a line integral, by the way, same line integral, and if you orient your curve backwards, all your DRs are the opposite of what they should be, and therefore you will just get the negative of what you would have otherwise got. Is that cool? Okay. So there's a weird little situation here. If you if you parameterize wrong, you don't get the right answer, but you know exactly how far off your answer is. It's off by a minus sign. And if you know exactly how far off you are, you can actually use that to compute what you actually need, right? So you can think of this as a measurement of how far you're wrong, or you can think of this as, hey, this is the little small price you have to pay. If you want to orient the wrong direction, just pay the very modest price of don't forget to multiply by -1, and it's actually kind of okay. Okay. All right, let's see one. Now I'm going to show you 4 different ways to answer this question. 3 of them are good. So it's the same as the previous question. We're just going to go clockwise instead of counterclockwise. Same curve, same vector field, blah, blah, blah. So the first 2 ways I'm going to show you how to do this, I'm going to literally parameterize the new correct direction. I'm just going to do that new correct parameterization in a couple of different ways to think about it. As usual, toolbox full of tools, right? Use the right tool for the right job. It's nice to have a bunch of options on how to think about things. So how would I derive, this direction here, clockwise? And one way to think about it is I can just choose for my parameter t to be like this. And now let's just think it through. Where am I when t is 0? Well, there's t. I'm not talking about theta. I'm talking about t, right? My time parameter that I'm choosing to set up, like so, when t is 0, I'm here. And then as t increases, I move clockwise as I'm supposed to. And then when t equals pi, I'm here. So if I could figure out how to do this geometry where that's t, then we're all good. And the way we do that, pretty straightforward, is to just recognize, well, that would mean that theta is pi minus t. Keep in mind that's theta, pi minus t. And then notice that position is nothing more than cosine theta comma sine theta. Good old polar theta. I just don't conflate your t and your theta. Is that cool? Everybody happy with that?
So then how do you switch it back to T in the neck?
Yeah, by memories of high school trig. In particular, here I use the angle addition formulas. Yeah, and so there's a little bit of algebra to be done to get from here to here. And by the way, just a reminder, I do need everybody to know angle addition formulas for sine and cosine. Just sine and cosine, right? And just the angle addition formulas beyond the obvious. Obviously, you need to know the symmetries, right, of sine and cosine, and Pythagorean identity, stuff like that. But make sure you do know the angle addition formulas, and that gets you from here to here. Cool. Okay, here's a different way to do it. Perfectly valid. Clever argument, too. If I want to know how to parameterize that curve like so, and if I remember, I already know how to parameterize counterclockwise, right? The blue parameterization, that's our old friend, right? That's cosine t comma sine t. And then I make the observation that, wrong color. Come on. These are just reflections of each other. Everybody see what I mean there, right? The orange curve and the blue curve, they are literally reflections of each other, even as they pass each other. They're reflections of each other over the y-axis. And of course, that reflection just introduces a minus sign on the x-coordinate of what I'm reflecting. And so you get the same answer either way. Is that cool? Also, I mean, what do you think? Does that make sense? Make sure to think through the details, right? Detail devils, very, very important. Okay. Whoops. Okay, here's a third way to do it, and I think really much better. And that is to say, well, I already know how to compute the previous curve that we talked about. I already worked out the full algebra on the counterclockwise oriented curve. And I already computed that on that previous curve, the integral's pi. Well, what I'm interested in is the same curve. It's the same curve with the opposite orientation, and that opposite orientation is just a minus sign in the answer. And so the answer minus pi. Much better. Right? I don't have to parameterize anything. I'd already parameterized it backwards, and I know that when I go backwards, that just costs me a minus sign. By far my favorite of the three ways that I've shown you so far. How are we doing? Is everybody happy with that? Everybody see how this is much nicer? Okay. All right. Okay, now here's the fourth way. And I say fourth way. I really don't like the following. I think it is fraught with problems. Keep in mind your goal when you're answering a question in this class. And by the way, I think any analytical class that you ever take, the goal is not to get the right answer. It's just not. The goal is to make a coherent, mathematically valid argument. Right? So the argument is what matters. Keeping that in mind. Some students like to make what I like to call time travel arguments. And they like to say, oh, well, I'm going the opposite direction along the curve, so it's like I was going from 0 to pi, but since I'm going the other way, it's pi to 0. Okay, well, all right. I mean, I get that. Right? And that will get you the correct answer. The reason this gets you the correct answer is because switching the bounds introduces a minus sign, and as we've just discussed, the minus sign is what you need to insert. That doesn't mean that this is the reason why. And so if you're going to make this argument, then you either have to persuade me that you have natural, experienced, unquestionable experience with time travel, which I don't think most people do, right? I'm big silly. Or you have to actually fill in the blanks on the argument. What's missing from the argument? And it's tempting to say, what's missing? Come on, that's what it is. It's pi to 0. I mean, what's the problem? Well, the problem is that if you're going the wrong way, that's not true anymore. And that's not true anymore also. So if you make an argument like this, you are using established formulas that we've set up that are no longer true. So that's not an argument. Right? Does everybody see what that's not an argument, right? Now let's talk about why is it, for example, that this isn't true? Well, your parameterization, if you don't change your parameterization, the parameterization is the same. It's still whatever it is. R prime is still going to be pointing the same direction as the original setup, but your actual velocity is not. So these are now negatives of each other. And, oh gosh, so there's a lot of stuff you have to rethink through everything in all of the setup that we've done. And it's just not worth the trouble, right? There's no need for that. Right? And not only is it not worth the trouble in general, It's definitely not worth the trouble when we already have a perfectly convenient, no mathematical issues at all. Look, opposite orientation means you're going to get the opposite answer. We've already talked about why that's true. There's no time travel nonsense in here. Right? So we already have a perfectly coherent, as convenient as can be, way to answer the question. We don't need to bring up questionable, highly fraught arguments. Does that make sense to everybody? I hope this makes sense. And keep in mind, again, as I said leading into this, when we're grading, right, we're not looking at whether you get the right answer. It's not what the course is about. We're looking at whether you're making reasonable arguments, and I think this is not it. Okay. All right. Enough of that. Okay. Yeah. Okay, so new question. Let's go way back here. This was our motivating example, our motivating sort of application. This whole idea of a vector line integral came up because we were considering how to compute work, and in particular, how to compute work with the understanding that the vector field represents forces. Right? Work is the result of moving through displacements while exerting forces. Okay. All right, so what if we have a totally different scenario? What if vector field F doesn't represent forces anymore? What if the vector field F now represents fluid flow? Force. So the question then is, okay, well then what does, as a result, this vector line integral, I can't say it represents work. How would it represent work? This isn't even a force. Right? Fluid flow dot displacement does not give work. So what does this give us? Does this give us anything meaningful? This is the question that I want to consider now. Okay. All right, and ultimately the answer is a physics concept that you very likely have not seen previously. And it doesn't even really quite have a name. Right? So this is a weird, somewhat unsatisfying little discussion. I'm about to argue how you should think about vector line integrals in the context of fluids, and you're not going to get that. Is it serotonin? What's that thing, that sense of satisfaction that you get when something, anyway, you're not going to get that because it's not going to be a single word answer like work. It's going to be a kind of a new concept, a new sort of construction to sort of think about. So the way I'm going to segue into this is I'm going to consider a different question. Here's the question. We have a curve over which we're going to eventually be doing a line integral. And I want to imagine that there is a certain amount of fluid in kind of a sort of the vicinity of that curve. In particular, imagine that I have an area sort of perpendicular to the curve, and I kind of drag that area along the curve, and that defines a sort of a tube-shaped region. It's not actually a tube, but it's shaped like a tube. Right? And that's the fluid that I want to talk about. That's what we have in blue. And the question is, to what extent, whatever that means, to what extent is that fluid flowing along the curve? That's the question. And again, we don't really have a name for this. So don't think about, wait a minute, what's the name for that? We don't have a name for it. But to what extent is that fluid flowing along the curve? The way we answer the question is very brute force. It's very just kind of write it down. But I've got lots of little pieces of curve. Lots of little pieces of fluid. There's one of the little pieces of fluid that's sort of near the curve. And I'm just going to write down, to what extent is that flowing along the curve? Now, not what is the velocity of that fluid. The actual velocity, the fluid itself is flowing, let's say, something like this. I'm not interested in the extent to which it's flowing overall. I just want to talk about the extent to which it's flowing along the curve, and that, of course, is a component. So flashbacks to chapter 1, somewhere along there. Is that cool? So you put this all together, and, so again, the total rate, we'll do it like this. The total rate that the fluid is flowing along the curve. Well, we're just going to take our dq here, and I'll take this, plug that in, and we can simplify as I've got there. Okay, and how does this help? What has this got to do with what we're interested in? We're not quite there yet. I want to make an observation about the answer we just got. The observation is the answer seems to depend directly on the area, and I'm going to say, well, of course it does. This cross-sectional area, the more area you have, the more fluid there is, and the more fluid there is, the more fluid is flowing along the curve, because there's more fluid, literally. Right? So the fact that this is proportional to area, I'm going to say, well, yeah, of course it's proportional to the area. That's obvious. So I'm going to change the question now. Now I'm going to ask the question, okay, obviously I know the area is important. So I'm going to ask now, what is, let's see, color choices. The rate of fluid flowing along the curve per unit area. Of course, per unit area, obviously it's proportional to area. Let's factor that out, and let's just talk about not Q, but Q per unit A, Q divided by A. And you notice the line integral. Weirdly, unexpectedly. Right? Who saw this coming? Right? Unexpectedly, vector line integral is the answer to this question. It's the answer to the question, per unit area, of course, what is the rate of that the fluid is flowing along the curve? In this sense, to what extent is the fluid, as it moves, to what extent is it moving along the curve? Overall, over the entire curve. So it's a weird take, right? It's a weird sort of concept, and this is something you just have to kind of sit with and digest. But that is the interpretation. If we're talking about a fluid flow and not a force, that's how you think about vector line integrals. And here's a closely related idea. If you're interested in a vector line integral over a closed curve, an important distinction. So a closed curve is a curve that starts and ends at the same point. Like here, maybe you say I'm starting there, and then notice it ends right back where it started. When you're talking about a closed curve, the vector line integral, we give a name to this. We call it circulation. That's a little bit weird. We don't have a term for the general construction, but when it's around a closed curve, this we give a name to, circulation. Okay, and so you can kind of see how this works. Here's our, let's look at our vector field. For example, in this picture that we're doing here, you can see how the fluid is flowing. And now let's just think kind of, yeah. Mm-hmm.
Why isn't it the curl?
Oh, that's why would it be the curl? Now it's good. Let me answer the question. It is going to be related to the curl. We're just not ready for that yet. Right, so there is a connection, good eye, right? But there's a lot more to be done before we can make that connection. And in general, the curl is more of a point-specific thing. Notice curl is defined at individual points. Here we're looking at a quantity that answers sort of an overall question. But close connection, absolutely. That's going to take us another couple of lectures to get to. Okay, so let's just kind of think through, hand wavingly. Here's my curve. My curve is going around like this. And wherever you might happen to be on the curve, hey, check it out. My fluid is flowing along the curve. And then I come over to here. The fluid is flowing along the curve. Everywhere I am on this curve, the fluid is flowing along the curve. So altogether, what's the combined extent to which the fluid is flowing along the curve? Well, I would say quite a bit. The circulation here is positive. By the way, notice we use lowercase Greek letter sigma to represent circulation. Then let's look at this next example. Very, very similar looking example, just very importantly, now the curve is going the other way. And same vector field, same fluid flow, and wherever you might happen to be on the curve is going like this, but the fluid is flowing opposite direction. To what extent is the fluid flowing along the curve here? Well, I'm going to say to a negative. It's going the wrong way, right? So there's a negative extent to which this fluid is flowing along that oriented curve. And add that up over the entire curve. Hopefully no surprise. Here the circulation is negative. Is that cool? And I'm seeing now we're out of time. So we'll draw the line here and we will pick up here on, exam on Friday. And so we'll pick up here on Monday. See y'all later. Have a good one.